In this video, we will be deriving the stiffness matrix for a bar or a truss element. We are going to consider the following bar or a truss subject to tensile forces. So we are looking at this element subject to tensile forces at its two ends. The length of this bar is L, and it has a constant cross-section A and a Young's modulus of elasticity E. We are going to consider this as a finite element that has two nodes, one at the beginning, node 1, and one at the end, node 2. The nodal displacements are given by u1 and u2, and they're both along the x-axis oriented along the length of the element. Corresponding to the nodal displacement, we have the element forces F1x and F2x expressed in the positive x direction. For this derivation, we are going to assume that the bar element has a constant cross-section area A, a modulus of elasticity E, and an initial length L. The bar cannot sustain shear force or bending moment. So written in terms of nodal forces, I can say that F1y equals to F2y equals to 0. This would also be true for M1 equals to M2 equal to 0. Any effect of transverse displacement is ignored. So the displacement is primarily along the x direction. Hooke's law applies. Axial stress is related to the axial strain. So we can say that sigma x is related to epsilon x via the Young's modulus of elasticity E. There are no intermediate applied loads. So we only have the loads at the beginning of the element, at the start of the element at node 1, and at the end of the element at node 2. Next, we are going to consider the stress-strain relationship within the element. So I can say that the stress sigma x is equal to E times epsilon x. And epsilon x is du by dx. For this element, if I'm looking at the total change within the length, I can say that in this element, epsilon x is equal to u2 minus u1 divided by L. From this, we can substitute here for epsilon x and say that sigma x then is equal to E multiplied by u2 minus u1 divided by L. By combining the strain displacement and stress-strain relationship, so here I have a stress-strain relationship. If I look at the equation of force in terms of stress, I have that F is equal to A times sigma. If I substitute for sigma, and of course here I'll be looking at sigma x, and the force in this case is equal to the tensile force. So if the stress is positive, it is in tension, so this is equal to T. So when we combine these relationships, we find that T is equal to A, and for sigma x, I'm going to put E, multiplied by U2 minus U1 over L. From the force equilibrium equations, if I look at my diagram here carefully, you see that F1x going in the positive x direction must be equal to the negative of T. So F1x is equal to minus AE over L multiplied by U2 minus U1. But if I look at F2x, it's oriented in the same direction as T. So F2x is equal to T equal to AE over L multiplied by U2 minus U1. I can rewrite these two equations simply as F1x is equal to AE over L multiplied by U1 minus U2, and F2x here is equal to AE over L multiplied by minus U1 plus U2. Next, we are gonna express these two force equations in matrix form, and clearly F1x, F2x are function of U1 and U2. So if I oriented and watch the negative signs, I'll get F1x, F2x is equal to AEL multiplied by 1 minus 1 minus 1, 1 multiplied by U1, U2. We now have the local matrix form that we have seen in the past chapters. The nodal forces F is equal to a stiffness matrix multiplied by the nodal displacement D. Therefore, the local stiffness matrix for a linear elastic bar is this K here, and looking at the equation, this is my K expressed as AE over L multiplied by the square matrix 1 minus 1 minus 1 and 1. So this gives us the stiffness equations for a bar element and the stiffness matrix also for a bar element. These may be applied to trusses that are connected by pins or are joint connected, allowing free rotation between truss elements. If you recall, we learned about the general steps of the finite element method. For any problem, the first step would be to discretize and select an element type. In this case here, we know that we are working with a bar or a truss element. So we have the type of element. We are going to postpone the displacement function, step 2, for the next section. But we've already defined the element relationships. We defined the element relationship. Simply here we had the epsilon x is equal to U2 minus U1 divided by L. And we also had sigma x equals to E multiplied by epsilon x. We derived the element stiffness matrix and equation. So we derived K to be equal to AE over L multiplied by 1 minus 1 minus 1 and 1. So this is the stiffness matrix. And we have the stiffness equation by being able to put it in matrix form as lowercase f equals to a K multiplied by D. And these are the element stiffness equations. Next, step 5 is where we are going to assemble the element equation to obtain the global equation and introduce boundary conditions. And as we have learned from the direct stiffness method, we can write the global stiffness matrix, this uppercase K, simply by superposition or taking the summation from E equal 1 to the number of elements n for all the element stiffness matrices K for each element E, where n is the number of elements in the structure. After we apply the boundary condition, as we're going to see in the following example, we can solve for the unknown degrees of freedom. So we have all the unknown degrees of freedom. Once we have the unknown degrees of freedom, we can also solve for the unknown forces and solve for the element forces. So once we have D well defined, I can solve for the unknown forces F, external forces, and I can then solve for the element forces F knowing D. Of course, once we have N, the stresses and the strains in the elements can be identified using the element relationship, and we should be able to interpret the results. So let's here look at an example of 3-bar elements that are connected together. Each of them is 30 inches in length. So this is a 3-bar assemblage. This would be element 1, this would be element 2, and this would be element 3. And I want to note here that all 3 members are oriented along the same axis X. This assemblage is fixed at the front and at the end, so we have a fixed support, so this is going nowhere. And it is subject to a force between element 1 and element 2. So we have a force here of 3,000 pounds. Element 1 and 2, elements 1 and 2, have an area that is equal to 1 square inch and a modulus of elasticity E that is equal to 30 times 10 to the power 6 psi. Element 3 has an area that is equal to 2 square inch and a modulus of elasticity E of 15 times 10 to the power 6 psi. And we want to solve this problem to find the displacements, the unknown support reactions. So find nodal displacements, specifically U2 and U3, support reactions, F1, and let me then take this opportunity and identify the nodes as 1, 2, 3, and 4. So we are going to be looking at F1 or trying to solve for F1 and of F4. And finally, we want to find the forces in each bar. We can think of these as internal forces, which, by the way, are the same as the element forces as we're going to see here in the solution. So the first step, after identifying clearly this is a 3-bar assemblage, so we are using bar elements. So if I'm going along my step, I know that I have a discretized system where I have 3 elements and 4 nodes, and the type of element we are using a bar element. We don't have to worry about step 2 for now. We're going to get to it in the next section, so I'm going to skip 2 and going directly to 3. We've already identified the relationship where epsilon x for each element would be equal to U2 minus U1 over L. So this is a strain displacement relationship, stress strain relationship. We have sigma x is equal to E times epsilon x. Step number 4, where we are going to be able to write the element stiffness matrices for each of these elements. So we have here Ke is equal to, for each element, AE over L multiplied by 1 minus 1 minus 1 and 1. So let's complete here step 4. Element stiffness matrices, lowercase 1, K1, is equal to the area is 1, E is 30 times 10 to the power 6 divided by the length, which is 30 inches, multiplied by 1 minus 1 minus 1 and 1. Clearly here the 30 and 30 would cancel, and we can say that K1 is equal to 10 to the power 6 multiplied by 1 minus 1 minus 1 and 1. And please remember that the stiffness here would have the same units as that of the AE multiplied by L. So remember that A is inch squared, E is pound per inch squared, divided by L, which is inch. So if you look carefully here, these two can cancel. So the units for K1 would be pound per inch, which, as we expect, is the same as the stiffness of a spring. K2 for element 2 would be the same as K1, and that would be 10 to the power 6, 1 minus 1 minus 1, 1, and again this is in pound per inch. As for element 3, K3, this would be equal to 2 for the area, 2 square inch, multiplied by E, which is in this case is 15 times 10 to the power 6, divided by 30, multiplied by 1 minus 1 minus 1 and 1. Again, I have 2 times 15, which is 30, is going to cancel with this, and I end up with the same stiffness matrix as elements 1 and 2. And again, 10 to the power 6, 1 minus 1 minus 1 and 1. This is pound per inch. So now I have written the stiffness matrices for my elements. I'm going to apply the direct stiffness method to assemble, to go to step number 5, which is, so if I call this here step 4, step 5 is to assemble the global stiffness matrix. I would like to remind you that we have these 3 bars. We had the nodes 1, 2, 3, and 4. We have element 1, element 2, and element 3. In order to apply the direct stiffness method, I want to label my element stiffness matrices corresponding to the degrees of freedom. Now, please remember that for bar elements, we have 1 degree of freedom per node. Makes things simple. So if I look at K1, for element 1 extends between node 1 and node 2, I can come here and put 1 and 2, 1 and 2. For element 2 extends between 2 and 3, so degrees of freedom here would correspond to 2 and 3, 2 and 3. For element 3 extending between 3 and 4, I can come here and put my corresponding degrees of freedom or displacement, 3 and 4. Now I'm going to use the direct stiffness method to assemble the global stiffness matrix, uppercase K. Looking at the structure, we have 4 nodes and 4 degrees of freedom or 4 displacements. So I expect to have a stiffness matrix that is a 4 by 4. So I'm going to label my rows and columns. We have 1 corresponding to displacements or degrees of freedom, 3 and 4. I have 1, 2, 3, and 4. Next, I'm going to start looking at the elements of the element stiffness matrices and assemble the global stiffness matrix simply by summing the stiffnesses of each of the elements and placing them to their corresponding row and column. So I'm looking at element 1, and I can use here different colors so you can see it. So for element 1, I'm just going to use the blue. So I'm going to go like, I'm going to take 10 to the power 6 as a common factor, and I'm going to put a 1, a minus 1, a minus 1, a minus 1, and the 1. So you can think of this here, the blue is for the first stiffness matrix. For the second, let's use orange here. So I'm going to look at the second, 2, and 3. So I'm going to come here and put a plus 1, a minus 1, a minus 1, and a 1 in row 3. And For element 3, we're going to use purple. So I'm going to come here and look at row 3 and 4, columns 3 and 4, and I'm going to have here a plus 1, have here a minus 1, a minus 1, and a 1. Everywhere else, we're going to put a 0. So everywhere else, we are going to be putting a 0. So I'll be putting here a 0, 0, 0, 0, 0, 0. So here I applied the direct stiffness method to assemble the global stiffness matrix. And this is the one we're going to use to write the global stiffness equations. Global stiffness equations can simply be written as uppercase F is equal to the stiffness matrix, uppercase K, the one we just assembled, multiplied by D, the nodal displacement for the total structures. So GSE stands for Global Stiffness Equations. In order to solve the global stiffness equations, we need to apply the boundary conditions. And for this problem, we had a fixed support at node 1 and a fixed support at node 4. This is to say that U1 is equal to 0 and U4 is equal to 0. So in my global stiffness equations, if I have these homogeneous boundary conditions where the displacement is equal to 0, and these are going to go corresponding to row 1 and row 4, this would allow me to cross row 1 and row 4 and column 1 and column 4. So when I'm looking at my simplified equations, I'm going to cross row 1 and row 4 and column 1 and column 4. And I'm going to be looking at this part of the global stiffness matrix when I write my simplified global stiffness equations or my modified global stiffness equations. So let's do that. So we are going to write modified global stiffness equations, and just to be clear, this is after applying the boundary conditions. So I have here my modified stiffness matrix, 10 to the power 6, and I have here a 2, a minus 1, and minus 1 and 2. Please recall that these corresponds to degrees of freedom U2 and U3, and they are going to be multiplied by the nodal displacement U2 and U3, and here this is equal to external forces. So again, corresponding here to U2 and U3, I think it's obvious. And corresponding to that, we are going to have the external forces F2 and F3. Now, we know that there is no force applied at 3, but the force that is applied at 2 is equal to a positive 3,000 pounds. So I can see here that this is equal to 3,000, and here it's a 0. We can solve for the displacements. These are simply two equations and two unknowns. So we can solve for displacements, and we'll find that U2 is equal to 0.002 inches, and U3 is equal to 0.001 inch. Once I have U2 and U3, I can go back to my global stiffness equations, the row 1 and row 4, the one that we deleted, and solve for the forces, the unknown forces. So solve for the unknown forces F1, this is 1, and F4. F1 would be equal to 10 to the power 6 multiplied by the first term is multiplied by 0 because u1 is a 0, and the second term here would be the minus 1 multiplied by u2, which is going to be 0.002. So I end up getting a minus 2,000 pounds. For F4, I'm going to have a minus, or 10 to the power 6, and then I have a minus 1 multiplied by u3, which is 0.001. So I end up getting a minus 1,000 pounds. So now we solve for displacements, we solve for the unknown forces, and next we want to solve for the element forces. And we are going to be using the element stiffness equations. For element 1, that extends between 1 and 2, I'm looking to solve for F1x and F2x. So if I write my element stiffness equation, we had lowercase f1x as it applies to element 1 and f2x applied to element 1. So these are equal to 10 to the power 6, 1 minus 1 minus 1 and 1 multiplied by the nodal displacement, which we have a 0 and we have a 0.002. When I solve, I find that f1x element 1 is equal to minus 2,000 pounds, while f2x element 1 is equal to plus 2,000 pounds. Clearly, the two forces are going in the same direction, but the element is either in tension or in compression. So they have to be equal and opposite, and that's why we have a negative and a plus. If you look at f1x at the start node as being negative, that would tell you right away that element 1 is in tension and it has a force of 2,000 pounds. Likewise, we can do element 2. And element 2 extends between node 2 and 3 and has the nodal forces here F2x element 2 and F3x element 2. Let's be clear here and say this is 1 and this is 1. Okay. So F2x element 2 and F3x element 2, these are equal to 10 to the power 6. 1 minus 1 minus 1 and 1. Please note that these are the element stiffness matrices. Multiply by the corresponding nodal displacement at 2 and 3. So I have here a 0.002 and here a 0.001. When you solve, you will find that this is equal to a plus 1,000 pounds and a minus 1,000 pounds. If the force at the start node is positive, it's pushing, going in the positive x direction, it's pushing node 2, and F3x is in the negative direction, it's pushing node 3, then we can conclude that element 2 or bar 2 is in compression of 1,000 pounds. And finally, we can do element 3 that extends between node 3 and node 4. So here we're going to be looking at F3x element 3 and F4x element 4. Of course, someone may look at it and say, well, we've already solved for F4, and we know that F4, the reaction force at the end of the bar is equal to minus 1,000 pounds. So that would tell us that this F4x must be equal to minus 1,000 pounds also, which is true. But we can also prove it here by solving using the element stiffness equations, and I should get the same result. F3x for element 3, F4x for element 3. This is equal to 10 to the power 6, 1 minus 1 minus 1 and 1. Multiply by the nodal displacement. So I have here a 0.001 at 3, and I have 0 at 4. And when you do the math here, you get 10 to the power 6. So I get here a plus 1,000 pounds, and here I get a minus 1,000 pounds as expected. So we can say bar 3 is in compression 1,000 pounds. So this example here illustrated how to use the element stiffness matrix of a bar element that we just derived to solve a 3-bar assemblage using the direct method, and assemble together the global stiffness matrix, apply the boundary condition to solve for unknown displacements, solve for the unknown forces, and solve for the forces in the members.